In 1975, Benoit Mandelbrot, French-American mathematician and physicist, solidified hundreds of years of research in mathematics and theoretical physics by coining the word fractal. And he illustrated this, his discovery with a graphical and beautiful graphical description, images. So you might be wondering what a fractal is. The word might be unfamiliar. It might remind you something in terms of fracture or fragmented, and that would be true. It has a connection with that. So let's take a look at what the fractals are and how we can understand them. The subject is quite complex and full of math and physics, but I'll try to explain it in lame terms, so to say. So there's a lot of fractal qualities in nature. Nature is full of fractals. One way to understand it is to think about different species of trees, for example. There are short trees, tall trees, thick trees, with small branches, big branches, and so on and so forth. But they all have certain similarity between them. They have a trunk, they have branches, and what science discovered is that they also have similarity in branching. So let's say you can see different kinds of trees, but all these are computer-generated models. But strikingly, they look pretty close to what the tree might look, maybe a little bit more curvy, and yet these are tree-generated models. So one of the properties of a fractal is self-similarity. So the self-similarity states that objects have certain similarity on many different levels. So a branch of a tree would resemble a whole tree, and a smaller branch would resemble a bigger branch, and so on and so forth. Another example is what a very well-known fern. You can see here that a branch has similarity on this level, and then even on a smaller level, I don't know what the divisions of a fern branch is, but you can see that this is similar to this, and then down to the smaller part is all reminds the main plant. Another property of a fractal is dimensions and iterations. So what is a dimension? To understand what dimensions are, we can talk about reproduction process in biology and maybe in photography, for example. So you can take a slide and you can make reproductions of a slide. You can print them on a photo paper and you have prints. And even though they all prints of the same slide, they would be slightly different. If you look, maybe one is slightly darker, another one slightly brighter. Same thing with copies of biological beings, plants or animals, humans. We make copies of ourselves, but each copy is slightly different. And in theory, this copying process is endless. So we can continue, and it also changes. So each copy is slightly different. So we have these constant variations, and we have also this endless recursion of the original metrics, so to say. Snowflake is another example. Not one snowflake is the same, and yet they all have similarities. They seem to have six-sided what do you call it? Usually, like they have 6 sides, but as you can see, the quality of water, the quality, the structure, how it was made, will determine the actual pattern and the design of each snowflake. So, talking about math part, so now that you can understand what fractals are in nature, we can go to a theoretical part. And this was one of the first fractals that was generated mathematically. It's a Koch snowflake. In 1904, this mathematician was thinking about these mathematical models, and he basically devised this mathematical transformation from a triangle to all the way down to this one, and you can endlessly increase the depth of detail. So there's self-similarity in this. This basically it continues on forever and ever. And in 1975, as I said, Benoit Mandelbrot made this print. It was much simpler black and white print that they made on a dot matrix printer in IBM lab. But it was basically the same kind of design. They call it kind of reverse Buddha or something like that. You can see that the self-similarity here is again a circle here, and a bigger kind of semicircle on the side. And you can zoom in any region of this image, and it will continue to be self-similar. It will continue to manifest the same kind of properties. Fractals are also a very old thing in culture. These are fractal patterns in African design. There's a lot of fractal design in Africa, starting from village design, where they have circular buildings in circular enclosures, and down to different games that have fractal properties, to divination and art as well. Fractals were known in India, where you can see the different temples were designed on one structure, and then similar structures were added around on each side. And in different kind of iconography art, again, you have a circle, what's called a mandala, where there's a symmetry and a self-similarity, where it's all kind of reflects onto itself. So what are the technological applications of fractals? Well, one of the amazing ones, and I'm sure you have it all right now, is the cell phone antennas. This is an example of a cell phone antenna using fractal design. What it does, it minimizes the amount of copper that's used for the antenna, because the surface is so small, but it still remains very efficient, even though it's a very small surface of the material that is used. It's also used in digital imaging and sound and image compression. So this is an image compression software that analyzes an image, and then based on analysis, it makes it groups the image, and then it compresses that, saving a lot of data and hard drive space. And one of my favorite applications of fractals is digital art. This is an image by one of the artists using his own software that he built. It's called Fractal Science Kit. I love that software. And as you can see, it's incredibly beautiful. You can see a lot of details, and everywhere you look, there's more details, and it's very symmetrical. There's incredible colors, and so on. And I happen to make fractal art myself. In fact, one of my images is on display at the library right now for the art exhibition show, student art show, and this is the image that's up there. If you find it, I'll give you a print of this work with my autograph. Limited to 3 people first. And then this is the original, and look what I've done. I applied another filter. It's called percolator. Basically, it's replacing lines with circles, and even though you can see some similarity, it's very different. This is another fractal of mine. And as you can see, there's a lot of different variations, and you can the creative amount of creativity is unlimited when you work with this. So to end this speech, I would like to remind what we were talking about throughout the speech. From brain cells to universe, there is a self-similarity between different objects. Rivers flow like snakes. Waves remind us dunes. This is a chemical process that is very similar to the skin of a fish. And all the way throughout, fractals are like a web that holds it all together.
Wow.